Here, we're going to investigate finding a locus. In this example, I have a point P, 5 cos theta, 4 sine theta on the ellipse, x squared over 5 squared plus y squared over 4 squared is 1. And it meets the x and y axes at A and B. M is the midpoint of A and B. And we're asked to find the locus of M as theta varies from 0 to 2 pi. Well, we're going to need the equation of the normal, which means that we need to start, as always, finding the gradient of the curve. Everything's in terms of theta, so we're looking for dy by d theta divided by dx by d theta. dy by d theta differentiating 4 sine theta gives me 4 cos theta, and 5 cos theta gives me minus 5 sine theta. So that's the gradient of the tangent. That means that the normal gradient is 5 sine theta divided by 4 cos theta. So now we want the equation. The normal equation is going to be y minus y1, 4 sine theta, is the gradient m, 5 sine theta over 4 cos theta, times the x minus x1, which is 5 cos theta. Multiplying up by 4 cos theta, we get 4y cos theta minus 16 sine theta cos theta is 5x sine theta minus 25 sine theta cos theta. Well, sorting all this out and writing down the right-hand side on the left, we've got 5x sine theta. If I subtract the 4y cos theta, minus 4y cos theta, and now I'm adding 25 to 16, or to minus 16, gives me 9 sine theta cos theta. So there is the equation of the normal. We're now looking for the points A and B. Well, at A, that is the point on the x-axis, y is equal to 0. Therefore, x is equal to sine theta cancels, 9 cos theta over 5. And so A is the point 9 cos theta over 5, 0. B, where it meets the y-axis, x is equal to 0. This tells me that y is equal to 9 over 4 cos theta cancels, so that's 9 sine theta over 4, and so B is the point 0, 9 sine theta over 4. We're looking for the midpoint, M. Is going to be, well, we add the x coordinates together and divide by 2. That's going to be 9, a half of 9 cos theta over 5. And adding the y coordinates together and halving, a half of 9 sine theta over 4. Let's take this point as x, y. Now here, it is a big help to use capital letters rather than small letters, because we're now using x to mean something other than what we meant by x earlier on. So using large X and large Y capital letters does help to keep us out of trouble. If we now look at what we've got there, we have that X is 9 over 10 cos theta, and that Y is 9 over 8 sine theta. If we want to find the locus of M, let's just make that look nicer. As a Cartesian equation, we've got parametric equations at the moment. We need to eliminate theta. Well, there's trigonometry around. You should be able to think of an equation which will help you to get rid of the theta. It's not a very difficult one. Sine squared plus cos squared is 1. So this is telling us that we want to get hold of cos theta is 10x over 9. Sine theta is equal to 8y over 9. Give myself a bit more room. Cos squared theta plus sine squared theta equals 1. That is 10x over 9 squared plus 8y over 9 squared. And I can rewrite that as x squared divided by 9 over 10 squared plus y squared divided by 9 over 8 squared equals 1. And that is an ellipse going through plus or minus 9 over 10, 0, and 0 plus or minus 9 over 8. Let's have a look and see how that comes out on a graph plotter. Here we have the ellipse, 5 cos theta, 4 sine theta. Here's the point P. I've drawn a normal, and it meets the axes at A and B, and there's the midpoint M. So we want to see what happens to M, which is the midpoint of the purple line, as P moves around the curve. It does appear to be doing what we said we would like to see, which was an ellipse. The ellipse, if you can remember, was one that went through point 9 on the x-axis and 9 over 8 on the y-axis. Well, let's have a look at that ellipse. There it is. That is the ellipse with the equation that we found just now. And if I move this point round, you can see that M stays firmly on that ellipse. So the locus of M, as theta varies, as P moves round the ellipse, is that smaller green ellipse there.